Okay. Good Lord. So the problems for this chapter are going to be one step further than our weak acid problems. One step further because we don't just have the weak acid, we're also going to have some amount of the conjugate base. But on a weak acid problem, we would have had this number and this Ka and nothing else. But because we have the weak acid and some amount of this sodium acetate, it's going to be a buffer as well. Not going to just be a weak acid. So now don't get me wrong. You can use the standard ICE table, the Ka expression, to solve for this. You don't have to use the Henderson-Hasselbalch. It's just the Henderson-Hasselbalch is a convenient rearrangement of that Ka expression to make this a little bit easier for you. So if you just plug in everything you know into the Ka expression and solve for H+, you're going to get the same exact number. So right here, pKa, so the negative log of this is 4.74. That's going to go right here. Then I'm just going to add on log of 0.5 over 0.32. Now, how this works, because 0.5 is bigger than 0.32, that's going to result in a positive addition to the pKa. So the pKa plus this 0.19 is going to give us our pH. So this is slightly above the pKa. So it's 4.93 is our pH of this buffer. 4.93, 4.94, depending on how you round it. Now, this guy, I forgot to hide the work, but we can see right here. This is a base, ammonium chloride and ammonia. This is a Kb. This is a Kb, means we're going to deal with a basic situation. Now, if you do it, the Henderson-Hasselbalch for a base, so this is POH equals pKb log of base on bottom, acid on top, you'll get the POH. But hypothetically, we could calculate the Ka from this and use the Henderson-Hasselbalch as we're given. So with this in mind, we can do this POH negative 1.8 times 10 to the negative fifth. That's 4.74. There's the ammonia, base on bottom, acid on top, 0.24, 0.45. We get POH of 5.02. And because I asked for pH, you have to subtract it from 14 to get 8.98.
How do we know which one is the acid and which one's the base from the second one?
You have ammonium, which is NH4, and ammonia, which is NH3.
Oh, okay.
So you had three. This one has one more hydrogen.
And it's losing. And it's giving it. It's losing it. Okay.
Mm-hmm. Now, hypothetically, what would happen if I did this like a acid instead of like a base? Since I don't have the work, I'm gonna quickly minimize this and show you. You could have done this the acid way and done it just the same. And that way we can show a little bit more work. So first thing you'd have to find is the Ka. So Kw divided by Kb is your Ka. So 10 to the negative 14th divided by 1.8 e to the negative fifth is going to be our Ka. So 1. So you get 5.56 times 10 to the negative 10th is the Ka. Take the negative log of that to get you the pKa. So right now our pH equals pKa plus log of acid over base. So our pKa is 9.25. Now we're adding the log of, look at this thing, how much, oh, wrong thing. How much ammonium did we have, which is our acid? 0.45. How much base did we have? That's ammonia. That's 0.24. So I do that. Log of 0.24 over 0.45 is negative 0.27. Negative 0.27 plus 9.25 gives us 8. If you round it, 8.98. If we look at this, what's our number? 8.98. So it doesn't matter which way we approach this. As long as you pay attention what we're getting at each step, you should get the same results. If you do it as a base, you're going to get a POH. You have to convert it to a pH. If you do it as an acid, you have to make sure you have a Ka, but you can get an acid you'd get a pH just fine. So you can approach this from the left, you can approach this from the right, you get the same result. That's just got to keep that in mind. Now, what was that? Okay. Now, the idea here is like, so the Henderson-Hasselbalch could be used with an ice table for a strong acid, strong base addition. That where some of these would come into play is that we're going to skip some of this stuff. I'll go through a bit of it, but I'm telling you, not a whole lot of this will be on the test. There might still be some of this in the homework. I haven't removed it yet. But essentially, where this chapter would be going is for titrations. What is actually happening in solution when you titrate? We'll say if we have 1 liter of 0.5 molar acetic acid and 0.5 molar acetate, and we add 0.32 moles of HCl, what adds to the pH? So I'm looking, here's the base, here's our acid, and I'm going to subtract moles from moles and add it to the other side, minus x, plus x. And so this goes up by 0.32 and this goes down by 0.32. And what would happen to the pH? So we could do that math and say, oh, what's happened? Well, we still have the same pKa, 4.74, but now it's, instead of log of 5 over 5, it's now log 0.82, log 0.18 over 0.82.
So but what is this finding?
This would find what is the pH after I've added this much acid.
Mm-hmm.
And so our pH would have dropped from 4.74 to 4.08. So this is where we started from. Oh my God. And then this is where it ends up at, saying like, if this buffer was not here, the second I add 0.32 moles of HCl, negative log of 0.32, it'd be a pH of 0.5. So if there's HCl and no buffer, we would have had a pH of 0.5. But because we have this buffer in there, the pH is only 4.09. So this buffer has neutralized the acid and kept it from having a large effect. Okay, so our first clicker question. Hopefully everyone's opened their clickers.
Oh, I don't have to.
Identify the solution with the best buffer capacity. So which of these guys can handle both acid and base the best? Which of these guys can handle the most acid and the most base?
Mine's not working.
Oh, God. Is it not loading or is it what?
I'm in. Like, it's working for me.
Mine just says it's checked. I've checked into class, but nothing else is coming up.
Hmm. We lost a participant too. Okay. You can always send me a private message of your results and I'll deal with that.
If you X out and then re-log in and rejoin, it'll restart.
There we go. Yeah. Okay, so, man,
How would you figure how would you figure this out? Would you have to put this? Would you have to put these numbers
no,
to a?
you this is one of those ones you think about. Think about if acid is neutralized by concentration of buffer, which acid could neutralize the most base? Which base could neutralize the most acid? So this is not something you actually have to do any calculations. It's like remember which one of these guys would be the most product favored if I gave you just values of Ka? Which one of these guys would be the most product favored? I give you values of Ka. You don't actually have to do the math. You could look at the size and tell. So we're just looking at the size and trying to determine which one of these guys can neutralize the most acid and the most base. Weird. I'm a hot mess today. Hot mess every day. Good Lord. Okay, I'll give you like 20 more seconds. So 3:10. So if you're in, make a guess. If you're not, send me an email, I guess, and I'll try to remember who all is here. So people don't respond. I'll mark you as being here but failed. But still, that's a half a point. Okay, that's more than enough. Okay, the correct answer should have been A, sadly. 1 molar means I can neutralize 1 mole of, if this is 1 liter, I can take care of 1 mole of acid. If this is 1 molar, I could take care of 1 mole of, what, this could take care of 1 mole of base, and this could take care of 1 mole of acid. All the other ones, this could only take care of a 100th of a mole, and 100th of a mole. 1 and 0.01. 0.01 and 1, you want the biggest of both numbers for the biggest buffer capacity. So some of these would be good only against base, but not acid. This would be good against acid, but not base. This would be good against neither.
Da-da-da, da-da-da.
Yeah. Okay. So we're going to at least look at these guys. I'm not sure how much math we'll actually do with this, but we'll at least look at these and look at, we will be looking at how to read a pH titration curve. I'm not sure how much actual calculations we will do. And I'm not sure how much we'll skip through. So, but there's 2 last parts of this chapter, talking about titrations and talking about solubility product, which is at the very end. So acid-base titration is the crux of the last 2 or 3 labs we're going to be doing. We're adding acid to base to neutralize them. At some point, we'll be reaching the equivalence point where the amount of acid and base equal. But now, since we're like we're titrating them stepwise, especially if we have a pH meter, we're going to actually look at how the pH is changing. So we care about more than just the end point. So now, hypothetically, had we another week, had we in-person classes, I'd go through ICE tables and Ka expressions, and we'll think about dilutions and a whole bunch of hot mess. This would be literally probably the hardest part of the class, because there's 4 or 5 steps you need to take into account each acid-base thing, each acid-base titration, because you're like, first, you have to calculate the moles of each thing. Second, you have to use an ICE table to subtract them out. Third, if it's a weak acid, you have to do the weak acid expression. Fourth, you have to redilute them. Fifth, then you have to calculate pH. So it is nothing anyone wants to look at. God's sake.
Oh, is that me?
Possibly. Okay.
Hello?
Why don't you mute yourself, for God's sake?
One sec, I'm in class.
Mute. Mute your mic. Okay. Strong acids. Okay. Man. Internet sucks. Okay. So the first thing we look is titration curves. These are beautiful. If you do them right, they would be really nice. If you eventually get to the second to last lab that I've posted online, there's a titration curve, and it's going to be a pain in the butt to record all the data. But then again, it was a pain in the butt to take all that data. So deal with it. So a titration curve, when you do this, you're plotting the amount of something added, whether it's acid or base, so the volume added versus pH. And so typically you're going to be either adding acid to base or base to acid. So now with the acid and base, there's not a whole lot we can fully determine except for the equivalence point. So what point does the acid and base equal? So you'll see, we see a very, 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 very gradual change in pH until we get close to the equivalence point. Then we start to shoot up, point where one drop is going to be from here to here. If you look at this with calculus, the rate of change goes to 0 at that point. And the rate of change, the acceleration, also goes to 0. This is called an inflection point. So you can actually calculate this and find out what is the exact pH, what is the exact volume at which the acid and base are equal, and thus pH is equal to 7. Now, being a strong acid and a strong base will result in being a strong acid and a strong base will result in this shaped curve. It's a gradual change, very little change, and equivalence point that is equal to 7. So these are really easy to determine whether it's a strong acid, strong base, and if that's the case, pH 7, and all you can determine is the equivalence point. You cannot determine the Ka. That's all we got. This one is a strong base, and I'm adding acid to it till we get to the equivalence point, and boom, it shoots down.
So the equivalence point, it's when it hits 0 or hits neutral?
When it hits 7 is when the pH is 7. The H plus and the OH minus are equal to each other. That's the point we're looking for. That's when the rate of change is 0. So this is going faster, 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 faster. We reach the max speed, and then I start turning down again. Then I slow down. It's like I go off the edge of the roller coaster, and then at this point we start slamming on the brakes so you don't slam into the wall at the very end. So we get max speed right here. And so the acceleration stops and the deceleration starts at that point. Now, technically, I've set my timer to go off. I'm going to risk it and see if it's going to try to kick me off or not. If it wants to kick me off and warns me, I'm going to may stop and we'll switch. But hopefully they got this sorted out where I don't have to stop this. We'll risk it. But for a titration, if we have to do any of these calculations, there's 4 points we'd look at. The first point is prior to titration. This is the easiest one. We have only acid, no base, or only base and no acid. During the titration, here's the pain in the ass one. The equivalence point for a strong acid, strong base, this is the easiest point. If it's a strong acid and a strong base, the answer is 7. Full stop, you're done. Because by definition, a strong acid plus a strong base, add the equivalence point, cancel out, so you have pH of 7. Then after the equivalence point, you would have to calculate that. I'm going to go, I'm just looking, seeing what we got. Oh, boy. Okay. Yeah.
We could always just call it a day.
No, there is at least one problem on the homework I'm going to go with. I'm going to leave this one in because I already did a video of how to do it. But if I'm going to look on the homework and see if there's any weak acid, strong base, or weak base, strong acid titrations, and I will remove those. But so how do you do this? How would you go about doing this? Even if we don't really cover this on the test, how would we go about doing this? Because of the nature of a strong acid, pH is going to equal the amount of H plus we have. And the amount of HA that remains is equal to the amount of H plus. So at the initial point where no base has been added, pH is just equal to the negative log of the initial concentration. That is not hard. That is something we've been doing all last chapter. So don't think that's not bad. Now, pH prior to the equivalence point is the one where you have to take some steps. Technically, when we do an ice table is supposed to be using moles. The reason we have not done this so far is because when we did an ice table so far, the volume has not changed. So if I calculate molarity and subtracted them, that would have been fine because the molarity did not change. I mean, the moles did not change, the volume did not change. But in this point, I have some amount of acid and I have some quantity of base. When I add them together, I'm changing the volume. So the volume initial and the volume final are different. So the concentrations will change even if a reaction did not happen. So we have to take that into account. So you can break down these into these 4 steps. 1, we calculate moles. Don't get stupid. Molarity times volume equals moles. Remember, if you leave it in milliliters here, don't forget milliliters there. But you can do it like that. But don't get stupid and forget, like, oh, this is what chapter 4, chapter 5 stuff from general chemistry. Don't forget how to calculate moles. Now, we're going to use the ice table. Now, in this case, the ice table is not going to be at X. We're going to know how much we subtract. We're going to subtract the limiting reactant. We're going to run the reaction where the limiting reactant subtracts the greater reactant, and we produce products. And everything that's left is what we're going to use later on. Step 3, we calculate the new concentration by dividing the moles remaining by the total volume. So if I added 25 mils of acid to 10 mils of base, we would have a total volume of 35. So we have to recalculate our dilution. Okay, so apparently I still have the time limit. Oh boy. Let's see. So I will finish this slide and maybe go ahead and, well, maybe I'll call this meeting early. When I run out of time, we're going to stop that. So we'll end today like 10 minutes early, and just rather than worry about that, hopefully we'll have this sorted out by next week. If we don't have it sorted out, I'm going to have to make some more phone calls. So we're going to calculate H plus using the dilution, and then finally this step is the same step we've always done. pH equals negative log of H plus. pH at equivalence point is 7, and then after equivalence point we do all the other steps, except now the limiting reagent would be the acid. We're going to subtract the acid, and whatever is left on the base is going to give us our POH. So it's the same steps we did before, except now there's an excess of acid left, and now there's an excess of base. But so hypothetically, we'll finish probably with this problem, and we'll use this as our jumping point. We have a homework problem kind of like this. So let me write this down on somewhere where I can work this out. Paint. Select all. Delete. Okay, so we have 25 mils of acid. We have 0.3 molar base, and it could take 13 mils to get equivalence point. We want to know 0, 5, 13, and 15. Okay. Okay, that's all we need. That's all we need. Now the first point, you'll notice, crap. We don't even have the concentration of acid, but I told you that it takes 13 mils to get to the equivalent point. How would we count the equivalence point of an acid? Well, MAVA equals MBBB. Molarity of acid times volume of acid equals molarity of base, volume of base. So if the concentration of the molarity of base is 0.3, the volume of base is 13, the volume of acid is 25, the molarity of acid must then be 0.156. So, okay. So, with that in mind, at initial point, at 0 base, the negative log of 0.5156 is 0.08. 0.81. So there's our
Wait, I
pH.
have a question.
Yes.
Is the 0.156 the Ka value?
No, there's
or
no
what is
Ka
that?
value. That is the concentration of acid. That is the concentration of acid, because it is a strong acid. There is no Ka at all. There's no Ka value at all.
Okay.
So we're just finding what is the molarity of the acid by knowing what is the equivalence point. At 13 mils, pH is just 7. 13 mils, the pH is just 7, because that's equivalence point. But so at 5 mils. So our ice table. So step 1, what is the moles of acid? The acid is going to be 25 mils times 0.156, or 3.9 millimoles. The base, which is 0.3, you say at 5 mils, 3.3 times 5 is 1.5 millimoles. C, we're going to subtract out the smaller number. So I'm going to subtract out 1.5. So at the end point, how much acid is left? We're going to have 2.4 millimoles of acid left and 0 amounts of base. Step 3, we're going to divide by our total volume. Our total volume is now 25 plus 5. 25 acid, 5 base, so 30 mils. So the molarity of acid is now 0.8, 0.08, 0.08. Final step, negative log of 0.08 is 1.09. So second point in the titration is 1.09. So we have pH starts at 0.8. After 5 mils, it goes to 1.09. Then after 13 mils, it goes to 7. Now, the last step in this is then how much, what's the pH after 15 mils? I got to erase, I'm just erasing. Now, the amount of acid stays the same. We still have 3.9. But now we have 15 mils of base. So 15 times 0.3 is now 4.5. 4.5. And when we subtract out the lowest number, 4.5 minus 3.9 means we have 0.6 millimoles of base. 0.6 millimoles of base divided by 25 plus 15, our new total volume. Our new total volume is 40. So 0.6 divided by 40 is 0.015. But when we take the negative log of this, this is not the pH. This is the pOH. So this gives us a pOH of 1.82. So 1.82, we have to subtract that from 14. So the pH is 12.1718. So these 4 parts in the titration curve, we have 0 pH, 0 volume added, 5 mils added, 13 mils added, then 15 mils added. I systematically followed those steps. Now, I have this worked out on a video on it's like, I think, God, I can't remember what number it is, like number 12 or number 4, something like that, on chapter 17. So we'll take a look at that video later, because there's a problem on homework like that. We'll work through maybe this one tomorrow, not tomorrow, Monday, and do that clicker. But I don't think we will do the calculations for weak acid, weak base. So that's all the time I'm going to have. I'm going to cut this class 10 minutes early, even though we started a little bit late, because it's such a hassle to splice 2 videos together. Thank you for your time. See you on Monday, guys.